All right, everybody. Happy Monday. Thanks for braving the really wet weather to be here. Um, so hopefully this will be more fun than getting wet in the rain. So we ended off here on Thursday. We talked about the net charges of this amino acid at pH 7 and pH 12. And then my last little bonus question for you to think about over the weekend was, can you figure out which pH at which this amino acid is a Zwitter ion, meaning it has a net charge of 0? So does anybody have any ideas about which pH that would be? You want to start us off? Yeah, it would be about pH 3. So let's talk about that in orange. Yeah.
It would really be anywhere 2 to 3.8, right?
Yeah, so you're referring to being in between these two pKs, right? So let's sort of true. Let's first start by talking about the charges of each group at pH 3, and then we'll talk a little bit about more how we arrive at the exact pH at which it's neutral. So at pH 3, so we'll start with our carboxyl group here, our pK1. So pH 3 is above the pK, which means it's going to be deprotonated. So we're still COO minus. Our pK2 of our amino group is 9.9. pH 3 is below that. So if our pH is below our pK, our group is going to be protonated. So we'll have NH3 plus, and then our pKr of our side chain is 3.9. pH 3 is below that, right? So our side chain is going to be protonated because the pH is below the pK. So this side chain is going to be protonated, have COOH for this amino acid, for this carboxylic acid. So those charges add up, right? This one's 0, this one's -1, this one's +1. That does give us a charge of 0 at pH 3, which is great. And to get a more exact, and we call this the PI, right, the isoelectric point of the amino acid. And the way we can get that is by averaging the two pKs that it falls between. So we're in between this pK 3.9 and this pK 1.99. So the actual isoelectric point of this amino acid would be the average. So we have 3.90 plus 1.99 divided by 2, which gives us about 2.95. Thank you to whoever said that. Yeah. So that's going to be our sort of exact pH where we're neutral. It falls exactly in between these two pKs. And the reason why we want to average it is because once you start getting close to the pK, if you think about a titration curve, right, our titration curve is flat around our pK, and that's where we have about half and half of our charged and uncharged species. So if we get too close to, for example, pK1, if we get, let's say we have if we're at pH 2, like right around exactly the pK, we're going to have some COO minus, but some COOH, right? We'll have like half and half. So instead of our net charge, so at pH 3, we want our charge to be -1. But if we get too close to pK, our charge will actually average out between -1 and 0 and be closer to -0.5. So that's why we want our isoelectric point to be, as far away as possible from the two pKs that surround it. That's why we average out those two pKs. Does that kind of make sense to everyone? You have questions about that? Okay. So let's think some more about titration curves now that your brains are a little bit warmed up. So I'm going to split the class into 3 different groups. Everyone is going to draw the titration curve for one of these amino acids, and then we'll all come together and discuss it together. So I guess we'll make it your left, so people on this side of the room can do threonine, people kind of down the middle of the room, you got lysine, people on the right, you got aspartic acid. So everybody take a few minutes and draw one of those 3 titration curves. And you can work in groups or with partners if you want. And if you have any questions, you can call me over and we'll all come back together in a few minutes.
Healing is a solar. No, there's no side. There's no PKR. For free, right? Just right. Well, we would only have for mine would be like something like that. We only have two. So mine is pretty like that. We only have the PKA for this. And then we have our two improvements. Yeah, three improvements like that. Yeah. This, here, yeah. The this would be the line basically. So this one here. I would have thought so. I don't think so either. So we have our 209 here. And then over here, it does that. 9.0. So everything's controlled. So these are blue ones. The purple ones and the blue ones are PK. We when you're below, you are native. I know this one. I'm not accounting for any of these numbers. Which ones? No, it just be that. That's just PK. The flag. Yeah, no, the flag one is. Yeah, no, it's this. That the blue ones are the PK, and the purple ones. That's what those are the. So do you just have like one large platform? So everything above. Yeah, above 2.9 would be oh, I don't know. I everything above here would be an H. Above 90 was NH2. So during this period, you have CO2 minus and NH3 plus. Under this, we would have equal voltage and NH. Now, what are the equivalence points? What information? What's how do you get equivalence points?
Equivalent point would be the
Double.
no, it's really the middle point. No, the half equivalence points for each PK. The equivalence point would be those.
No, that's a PK. Right.
All right. Seems like most people have something drawn, maybe some more confusion, some more confident. So let's all go over them together and hopefully we will all be less confused by the end of this exercise. Allegedly, yeah, exactly. So first up, we got threonine. So does somebody from the left side of the room want to volunteer to draw a titration curve? You're being voluntold that you got to draw the titration curve.
I gotta draw this.
All right, go team left.
Team left. Got it. This is a lot prettier than my thingy. That's kind of cool.
Yeah, you might want to plot some points first, or you can just freehand it. That's up to you.
Yeah. I forgot the numbers. It was 9, right? The second equivalence point?
I think I wrote it. Yeah, 9.1.
Okay.
I don't think I can do that. I just take the W on that one. No, that'll be for control.
I think that's right.
All right, excellent. Let's go. Let's see what everyone else thinks. Yeah. Yeah. Round of applause for our volunteer. Yeah. All right, so let's go over how we arrived at this beautiful titration curve. So you did a great job plotting out our two pKs at the half equivalence point, right? So our first pK is about 2.09. Our second pK, our second half equivalence point is at 9.10. And then you correctly showed at the actual equivalence points, the line get very steep. And those equivalence points are about halfway between the two pKs. So when you plotted this, you could have drawn like an additional mark sort of halfway between the two pKs at your first equivalence point, and then your second equivalence point just goes kind of off the chart. So let's talk about what each of our ionizable groups looks like at each of the relevant points on our titration curve. So at the very beginning of our titration curve, I guess first of all, what are the ionizable groups in this amino acid? Anybody? What are the ionizable groups in threonine? Yeah.
The carboxyl
Exactly. Yeah. So we got the amino, we got the carboxyl, and there's no ionizable side chain, just the two groups. So that's why we got our two pKs, our two equivalence points. So right at the beginning here, before we get to our first pK, our pH is below both pKs, right? So for our amino group, what would that look like? Like what charge would it have, or how many protons would it have? Would it be protonated, deprotonated? Yeah, it's protonated. Yeah, so our amino group would be NH3+. And what about our carboxyl group? It's also protonated, right, because we're below both of our pKs. So the amino group, when it's protonated, has a charge of +1. Carboxyl group, when it's protonated, is neutral. At our first equivalence point, that's where things start to change, right? So we've passed our first pK. Is our first pK for the carboxyl or the amino? Carboxyl, yeah. So what happens to our carboxyl group's charge now at the first equivalence point? It's deprotonated. Yeah, exactly. So our carboxyl group is now deprotonated, COO-. Our amino group, we're still below the pK for our amino group. So what does our amino group look like? Protonated, deprotonated? Protonated, exactly, because we're below the pK. And then our second equivalence point, now we're above both pKs, right? So what does our carboxyl group look like at our second equivalence point? Protonated or deprotonated? Still deprotonated. And what about our amino group? Yeah, it's neutral because it's deprotonated, exactly. So now you can, once you know these, you can start filling in what your half equivalence points look like, your actual pKs. So for our first pK, that's the pK for our carboxyl group, we're in between our protonated and deprotonated forms. We have exactly half and half of each at the pK. That's what defines the pK. So you'd have half COOH, half COO-. But for our first pK, the amino group is still always protonated. Our second pK, now this is where our amino group is at half and half, right? We're halfway below there, we have protonated. Above there, we have deprotonated. Right at the pKa, we have about half and half. But for our carboxyl group, we already know that it's deprotonated over here. So now, once we know what our functional groups look like at each of our equivalence points and half equivalence points, we can also figure out where our different charges are at different pKs. So, like at 0 equivalence, like before our very first equivalence point, we have a total charge of +1, right? Because we have our positively charged amino group, our neutral carboxyl group. At our first equivalence point, we have one of each, right? We have one positive charge, one negative charge. So our overall charge is 0. We're neutral here. At our last equivalence point, at number 2, we have one negative charge and one neutral charge. So we're at -1. So then now we can then start filling in between our equivalence points. So at our half equivalence point, at our first pK, we're halfway between 0 and +1, right? So we have about +1/2, because we have our +1 from our amino and we have our -1/2 from our carboxyl. So that gives us about +1/2 if you add them together. And then for our second 1.5 equivalence point, we are at -1/2 for the same reason, right? We have our -1 coming from our carboxyl, and we have our +1/2 coming from our amino, gives us a total charge of -1/2. So what pH is our isoelectric point for our amino acid? Yeah. Yeah, exactly. It's right in the middle here. I actually forgot to do the math on that, but it's exactly halfway between our two pKs. So if this one is 2.09 for our first pK, our second pK is 9.10. You can average those out, and you will get something around 5.5. I did not do the exact math on that. Does that make sense to everybody? Any questions about that? All right. So, do we have a lysine volunteer? Yeah. Oh, you have a question? Okay.
Sorry. Can you explain the relevance of the
Yeah, I mean, it's the point at which it's the pH at which your protein has no charge, so that will affect how it interacts with its environment. So if you think about something like we'll talk about in chapter 5, like with column chromatography, if you wanted to do ion exchange chromatography, it's important to know at what pHs your protein might be positively charged, negatively charged, or neutral. So that's sort of a practical example. It's often helpful to know sort of when your protein will be interacting with other things, what other things it might interact with. And at the isoelectric point, proteins are generally their least soluble, right? Because they have no net charge, so they're sort of the least able to interact with water. So yeah, that's a couple of useful things about it, I guess. Yeah. Yeah. Any other questions about titration curves or threonine or anything else? Yeah. So in this case, yeah. So for amino acids that don't have an ionizable side chain, yeah, pretty much always when it's a zwitterion, it's going to be the isoelectric point. That doesn't. When you start having ionizable side chains, that might change, and we'll see that with our next two examples. Yeah. For an amino acid with a non-ionizable side chain, yes. When you start having ionizable side chains, depending on the pK of the side chain, the pH at which it is neutrally charged might be different. Yeah, because it's not necessarily, there's more than one pK, so it depends which two pKs you're between when it's neutral, and when it's neutral depends on what each functional group is like when it's protonated or deprotonated. So like, for example, with amino groups, when they're protonated, they have a charge. They're positively charged, versus a carboxyl group, when it's protonated, it's neutral. So it's more than just thinking about, are you above or below the pK? You have to consider both the pK and what the functional group is and what charge it has when it's protonated and deprotonated. All right. Any other questions? Okay, so let's do lysine. Do we have a lysine volunteer? Should start offering candy or something to incentivize you guys to come up here.
That's the oldest trick in the book.
Right?
I don't think I've fallen for that one again.
Oh god, this is weird.
Maybe if it's good enough candy, right?
Okay, let me draw the points first.
Yeah, so it might help to plot points first,
Yeah.
and then fill in the line after.
That's horrible. Oh wait.
Nice. Excellent. Good save. All right, so now we have our lysine titration curve. So we can go through and fill in the blanks, kind of like last time. So our first half equivalence point, that's where our pK1 is for our carboxyl group, right? And we know that our pK1 is 2.16. Our next half equivalence point is our pK2 for our amino group. And that one is 9.06. And our last half equivalence point right here is our pK for our side chain. The pK for our side chain is 10.54. Okay. So, yeah, so now that, sure.
So the buffer range that we usually talk about is plus or minus 1 right? And so in this case, since those PKs are within like plus or minus 1 page of each other,
Yeah.
Just, like, would it not just be like one large block part?
Yeah, in this case, you might end up having a sort of very large, messy buffer region. Yeah, I mean, if you just had a solution of like pure lysine, I guess that would probably happen. Yeah, I mean, most of the time when you're making a buffer, it's not usually like using an amino acid as the buffer. And usually when you have a protein or a peptide, you have multiple different amino acids, and so it actually gets much messier the more amino acids you add on, right? But yeah, that's a really good point, something to think about for sure. And we'll definitely keep that in mind as we go through the charges for this molecule. Yeah, for sure. Okay, so our sorry, I'm grabbing color. Yeah, so our equivalence points are going to be halfway between our pKs. And like you mentioned, the second equivalence point is kind of real short. But so we have these points that are in between all of our pKs. So what functional groups now do we have that are ionizable? So we have our amino and our carboxyl, just like for any amino acid. And then lysine, as you notice, it has 3 pKs. It has an ionizable side chain because the side chain itself can also be protonated and deprotonated. So let's just remind ourselves what the structure of lysine looks like by looking at this picture. And so essentially our lysine has an extra amino group on here, and that's what contributes to our pKr. So our third ionizable side chain is also an amino. All right. So at our 0 equivalence point, we are below all of the pKs, right? All the pKs are above this very 0 equivalence point. So our amino groups would both be, or everything would be protonated, right? So our amino groups would be protonated. They'd have a positive charge. And our carboxyl group is also protonated, and that makes it neutral. That's at our 0 point. Can anybody tell me what our functional groups would look like at our first equivalence point? Yeah.
2 NH3 pluses and 1 CO.
Yeah, exactly right. So our amino groups, we're still below the pKs for both of our aminos. They're both going to be protonated, but now we've passed the pK for our carboxyl group. Our carboxyl group is deprotonated. We've got a negative charge. All right, so what would we have at our second equivalence point? Yeah.
1 NH3 plus, 1 NH2, and 1 CO minus.
Yeah, exactly right. So we passed one of our pKs for one of our amino groups, so that one is now deprotonated. Our second amino group is still protonated, still charged, and our carboxyl group remains deprotonated. And then what would we have at our third equivalence point all the way at the end? Yeah. Exactly. Yeah, so now we've passed all of the pKs. Everyone is deprotonated. So our 2 amino groups are neutral, and our carboxyl group is negatively charged. So now that we know what's going on at our equivalence points, we can then fill in what's happening at our half equivalence points, where our pKs are. So our first pK, which is for our carboxyl group over here, we would have half protonated and half deprotonated, right? We're right in between. So we have some COOH, some COO minus. And what would our amino groups look like here? Yeah, they're all protonated, exactly. And our second half equivalence point, now what would we have? Yeah.
All of them, all the carbons are going to see
Uh-huh.
and then half of the amino, the first one of the amino groups are going to be NH2 and then NH2 plus, and then the rest are going to be NH2 plus.
Exactly, yeah. So one of our amino groups is at half and half at this point. So we have some NH2, some NH3 plus, and our other amino group is still fully protonated because we're still below pKr. So what would we have at our 2.5 equivalence point? Yeah. Mm-hmm. Mm-hmm.
And then the side chain would be half NH3 plus.
Exactly. Cool. So now we know, now we have enough information to figure out our charge at each of these points. So at our 0 equivalence point over here, we have 2 pluses and a neutral, so we're at +2. At our 1 equivalence point, we have 2 pluses and a minus, so we are at +1. At our 2 equivalence point, we have a plus, a minus, and a 0, so we're at 0. And our last equivalence point, we have 2 neutrals and a minus, we're at -1. And then we can fill in the in-betweens as well. So at the first half equivalence point, we're halfway between +2 and +1, we're at +1.5. At our 1.5 equivalence point, we're halfway between +1 and 0, we're at +1/2. And at our 2.5 equivalence point, we're halfway between 0 and -1, so we're at -1/2. So where is our isoelectric point for this amino acid? Which one? The third equivalent, over here. That's the third. So yeah, this one is, it's kind of confusing. This one is counted as 0. Yeah, it's the second equivalence point. Great. So this is our isoelectric point, and it's halfway in between those two pKs, which, like Suhani mentioned, they're very close to each other, so we might have a broader region in which we have maybe weird partial charges, but we can just, do our best. So we will just average out these two. So we have 9.06 plus 10.54 divided by 2. So it's, yeah, somewhere around 9 3/4, 9.8. Thank you. Cool. Any questions about lysine? Yeah.
I just want to be trying to clear on this.
Okay.
I understand for the PK2, what is the extra NH3 plus on top represent?
For this one?
Yeah.
So that's the side chain amino group. Yeah, so it's confusing because there's the regular amino group at PK2, and then the side chain is also an amino group that's also ionizable.
The NH2, the one that's assigned, that's the second one.
Yeah. Yep. Yeah.
The definition of a zero ion, as far as my understanding, like when the net charge is 0.
Yeah.
So wouldn't the isoelectric point always be where it is
Yes, that is true. Yes.
And so I guess my question is, what is different between lysine, for example, and uranium having that extra side ionizable?
Yeah. Yeah, I mean, I guess it's more sort of, you had to consider at which equivalence point it is a Zwitter ion. That's what will change. So at lysine, it's at our second equivalence point at which it's neutral. At threonine, it was at our first equivalence point.
So, okay, the equivalence point number.
Yeah, so like with the equivalence point will change. Yeah, you're right. Sorry. The definition of a Zwitter ion is when it is neutral, which makes it the PI. Yeah, that was, yeah, I did not explain that very clearly. Yes.
And like numbering, like the equivalence points.
Yes.
The 0, 0 point is always your 0.
Yeah. Yeah, it's when you have not started titrating yet. You're at your lowest pH, and we're talking about equivalence of base that we're adding.
Thank you.
Yeah. Yep.
Also, kind of add on to that. So then the pH that amino acid neutral is equal to the pI, even if there's that R.
Yeah. So the pH is the pI when the amino acid has a net charge of 0. Yes.
So even with the ion acid.
Yeah. It's not as simple as just like averaging out the carboxyl and the amino. You have to take the cytene into consideration to figure out what that pH is. But yes, that is the pI, whatever that pH is.
So then,
Yeah.
for lysine at pH of 9.8, we would say that it's physiological.
I mean, that's its pI, it's an isoelectric point. So when you talk about physiological pH, that usually just refers to the pH in like your body. So it's around 7.3 usually, 7.2. Yeah.
So
No worries. Yeah.
Is the pH for like this amino acid for it to be neutral, would it be 9.8?
Yes.
Okay.
Yeah. Yeah.
Can you find the pH necessary to be at the first equivalence point by averaging out the first of pK?
Yes. Yeah. You can always figure out the equivalence point pH because it's halfway between the pKs on either side for any equivalence point. Yeah. Yeah.
So why is PI 5.36 plus 10.2? We don't include 2.16.
We don't because of the way the charges are. So the pi is where we have a net charge of 0. So when you go through at each equivalence and half equivalence point, you look at the charge of each of the functional groups. So in this case, we have 2 amino groups and a carboxyl group that are ionizable. And so we figured out that it has to be at equivalence point number 2, where it comes out neutral, because you have a +1, a -1, and a neutral. And that's where it's 0. So that's how you know you have to then average out the pKs on either side of that.
Okay.
Yeah. Any other questions about lysine? All right, let's do aspartic acid. Any volunteers? Go for it. Come on down. Don't be scared, it's fine. Yeah, so I recommend first just plotting points, yeah, and then just throw a line to connect them. I'm sorry. No, you're good. No, I will always I'll give you a table of them. And before the exam, thank you. That looks great. I'll post the sheet of like what you'll have on the exam for reference, so that way you'll know what you'll have and what you won't have. Yeah.
When is our date for the second?
The 5th. Yeah, so it's a week and change from today. Yeah. Yeah, so Monday, so the goal for today is to start chapter 5. On Thursday, we should get through most or all of the rest of chapter 5, and then Monday we'll finish whatever we didn't from chapter 5 and then review. And we will not have, so tonight quiz 3 is due, Thursday quiz 4 is due. There will be no more quizzes until your exam, which is next Thursday, October 5th. The 5th quiz will be after that exam, about whatever we do after the exam. Yeah.
What's the format of the test? Is it mostly short answers or multiple choice?
It'll be a variety. It'll look sort of like what you see on the quizzes. So some sort of fill in the blanks, some matching, some multiple choice. I won't, have an essay or anything like that. You may be expected to draw things. Be able to like draw a titration curve, for example. Yeah.
Should we be able to like Google some? I know we focus on the function, but give us a lot of questions on
like organelles and things. Yeah. Definitely know what they all do. I won't ask you to like draw a cell like accurately or something like that. That would be a lot. That would require drawing skills. Yeah. Yeah, so about, hopefully by this Thursday, I'll sort of get a sense of like what we've been able to cover, and then I will post like an exam set of practice questions like we've been having for the quizzes, and those should be pretty similar to what you'll see on the exam. And then I will also post the reference sheet that you'll be getting on the exam. Okay. Yeah. So let's talk about aspartic acid. So we have our wonderful titration curve. So our half equivalence point is our first pK, which is 1.99. Our next half equivalence point is our pK2, or sorry, it's actually our pKr, which is 3.9, and our last half equivalence point is our pK2, which is 9.9. So let's figure out what our three ionizable groups are, right? So we always know our pK1 and pK2 are carboxyl and amino. So what is our pKr? Let's look at our picture of aspartic acid. So as you might guess from the name, it's a carboxyl group again. It's carboxylic acid. So now we know our side chain is another carboxyl group. So what are our, sorry, I'm picking a color and I can't talk and pick at the same time. Yeah, so at our zero equivalence point, what would our, it's not the color I wanted, what would our three ionizable groups look like? We're below all of the pKs. So is everything protonated or deprotonated? Everything is protonated, yeah. So what would our two carboxyl groups look like? Yes, they would look like carboxylic acid. They would be COOH, COOH. What would our amino group look like? It would look like NH3+. Thank you. And that's at our 0 point. And what would our charge be here? Our overall charge? +1. Thank you. All right, so what would we have at our first equivalence point? What would our amino group look like? Yeah, it's still protonated, it's still NH3+. So we passed our first pK, so that means which group has now become deprotonated? Yeah, the backbone carboxyl group, exactly, is now deprotonated, but our side chain carboxyl group is which way? Still protonated, exactly. So what would our charge be here? It would be 0, yeah. Because we have a neutral, a negative, and a positive. So what would happen at our second equivalence point? Yeah. Yeah, exactly. So now both of our carboxyls are fully deprotonated. What about our amino group? It is still protonated because we're still below the pK for our amino group. So what would our charge be here? It would be -1, yeah. Okay, so let's talk about our third equivalence point. Now we've gone above all of our pKs, so everything should be fully protonated or deprotonated? Deprotonated, yeah. So our amino group is now NH2, it's deprotonated. Both of our carboxyl groups are deprotonated. So what would our overall charge be here? Yeah, -2, yeah. right, so now we can fill in our half equivalence points. So at our first pK, our first half equivalence point, which group is half protonated, half deprotonated? Yeah, the carboxyl group that's on the backbone, exactly. So we have half deprotonated, half protonated. Our other side chain carboxyl group is still fully protonated here. Our amino group is also still fully protonated here because we're far below its pK. So our net charge is going to be +1 minus about a half, so we're at about +1/2, right? Our second half equivalence point, now we've already fully deprotonated our backbone carboxyl group. So which group is at about half and half at our 1.5 equivalence point? Yeah. Yeah, so our side chain carboxyl group is half and half. And our amino group is, we're still well below the pK, so it's still fully protonated. So now our charge is somewhere between 0 and -1, so it's about -1/2. And that brings us to our last half equivalence point at our pK2. And that is the pK for which functional group? The amino group, yeah. So at this point, both of our carboxyls are fully deprotonated. And what does our amino group look like? Yeah, exactly. It's half protonated, half deprotonated. So we have an overall charge of about what? Yeah, -1.5. Cool. So where is our PI now? Which equivalence point? Yeah, so our PI is now at our first equivalence point. That's where our net charge is 0. So what would be the approximate, how would we calculate the approximate pH of that? Yeah. Whoops. Can't draw anymore. So that's something like what, 2.9 or something? Yeah. All right. Any questions? Yeah.
Sorry, I still have to
Sure.
The half equivalence point is where we do the Henderson muscle up, or is that where that's where the pH is equal to pH because it cancels?
Yeah, so at the half equivalence point, the pH is the pK, and that's where you have about half and half of the ionized species. You have half protonated, half deprotonated at the pK, which is at the half equivalence point. So they're called the equivalence point because you are fully protonated or fully deprotonated at an equivalence point. When you're at a half equivalence point, you're kind of halfway in between the protonated and deprotonated form. Yeah.
So you said at the equivalence point, the pKa equals the pH.
At the P. Sorry, say that again.
I might have misheard you.
Okay.
I thought you said at the equivalence point, the pKa equals the pH.
At the half equivalence point. Yeah. So at the half equivalence point, that's where your pH is your pK. So that's why when we draw our titration curves, we can start by plotting our pKs at the half equivalence points. And then you can start filling in at the full equivalence points, pHs halfway between those pKs. And then you know the shape of your curve because around your pK it's flat, and around, which is the half equivalence point, and around the equivalence point it's pretty steeply vertical-ish. Yeah. All right, any more questions? Okay. Let's talk about peptides. So, when two amino acids join, what kind of bond is formed? Yeah, it's a peptide bond. And do we know another name for that type of bond, like a more general name? I'm sorry? It is a covalent bond. So like let's look at a peptide bond. So like this is, I don't have a good picture of this. Yeah, it's an amide bond. Sorry, I was trying to find a better picture, but I don't think I actually have one in this particular slide set. Yeah, so it's a type of amide bond. An amide bond is a less specific name. That's anytime you have something like this, right? You have a carbonyl next to an amino. That's an amide bond. Peptide bonds are between two amino acids. They are a type of amide bond. They are also a covalent bond, yes. This is why fill in the blanks are very tricky, because there are many right answers. I mean, it's not wrong, yeah. It just, you can be as specific or as non-specific as you want, I guess. Yeah. That's tricky. Yeah, I feel like I would probably word an exam question a little differently to try to get the answer I wanted. This would not be a good exam question. So what do we lose when we join together two amino acids to make our covalent bond? That's an amide bond. That's a peptide bond. Yes, we lose a water. Exactly. Which is also, as we learned, a condensation reaction, right? You could have also said it's a condensation reaction. But I guess that's not a type of bond. It's a reaction. So, all right. So a peptide has two ends. What are the names of the two ends of a peptide? Yeah. Exactly. Yeah. The end, terminus, and the C, terminus. A lot of times you'll see people will just write N term or C term. It's short for terminus. It's just faster. Okay, so a peptide sequence is always written in which direction? Yes, it is written in the correct direction. Excellent. Yeah, I heard someone shout it out, the N to C direction. So when you look, that's why when you look at a peptide, it's important to identify where the backbone is with your amino group, your alpha carbon, your carbonyl carbon. You can trace along that, and then you can figure out which end is the amino end and which end is the carboxyl end. The amino end is where the first amino group is that hangs off one side. Carboxyl, C-terminus end is where the last carboxyl group hangs off at the end. Any questions about these terms? Okay. So now that we've gone over what a peptide looks like, let's look at this peptide. So take a couple minutes, figure out how many amino acids are in this peptide, and write out what is the sequence of amino acids. You can use like the table of amino acids that is on Brightspace. Maybe I can pull it up for you while you work on this. And I'll give everyone a few minutes to think about this. I'll project the table so you have something to look at. Hold on a second. Oh, me. Okay. Here's amino acids. That should be all of them. Yes, yeah, that's the hard part about this. Maybe I don't know. Surprisingly difficult to project multiple things. Alright, let me move this over. Of course it's not behaving. Everyone can share. How's that for everyone? Okay, so hopefully everybody has some ideas for what we're looking at. So, first question for everyone is how many amino acids are present in this peptide? Yeah, 3. Yeah. How do you know? What did you count? Or
I just kind of drew it out and did little dehydrations between the first carbonyl, carbon, and amine.
yeah.
Kind of went close to that.
Yeah, excellent. So basically, if you're ever looking at a peptide and don't know where to begin, start by finding the backbone, your amino groups, your alpha carbons, your carbonyl carbons, and follow them along. So for here, you can start on the left. We have an amino. Maybe that's our beginning. Amino goes to carbon, goes to carbonyl. Seems like one amino acid, right? Then next to that, we have another amino group next to a carbon, next to a carbonyl, right? Another amino acid. And then we have our third one over here, amino group, carbon with the side chain, carbonyl carbon. So our backbone is in red. And then once you have your backbone, you can then find where the alpha carbons are, because your alpha carbons have the side chains, and that tells you the identity of the specific amino acid that you have. So our alpha carbons, we'll circle them in green. They're always in between the amino and the carbonyl, right? So here's your first alpha carbon. Here is your second alpha carbon. Here's your third alpha carbon. And then, of course, the things that were not highlighted are peptide bonds, right? So the peptide bonds are those little amide bonds in between our carbonyls and our aminos, right? So now hopefully it's a little more clear. We have 2 peptide bonds connecting 3 amino acids. Yeah.
Also consider like the peptide bonds part of the backbone.
It is. Yeah, I just wanted to point them out in case you wanted to count them. But yeah, they are certainly connecting together the piece of the backbone. Yeah. Yeah. But yeah, in terms of just counting, if you see, usually if you have a linear chain of amino acids, you'll have 1 less peptide bond than the number of amino acids you have. So if you had 7 amino acids, you'd have 6 peptide bonds. Yeah.
I'm going to say the sequence.
Okay, yeah. What's the first one?
Aspartic acid, valine, cysteine, I think.
Yeah, excellent. Yeah, so the first one is aspartic acid. Also known as ASP or D, if I have that correct. And that's, make that another color. Here's our aspartic acid side chain. Our next side chain is valine, or Val, V. And our last side chain is cysteine, or cis, or C. So if you wanted to write out this whole sequence, you would write it as DVC, or ASP, Val, Cis, however you like it. Yeah.
On our table,
Yeah.
do we get the short one?
Yeah, it'll look just like the one I was projecting. So let me pull that up for a second. So yeah, so here's our aspartic acid on the bottom. Where's my pointer? So it'll look literally just like this. This is what you'll get. Yep. Yep. All right. Any questions about our little peptide? Okay. So now let's talk about the charge of a peptide. So we did a couple problems finding charges of functional groups on single amino acids. We also looked at a longer peptide. I'll kind of bring it together. So we have this peptide here. There are 7 amino acids in it, if I'm counting right. And so at pH 7, how many charged groups are present on this peptide, and what is the net charge of the peptide? So I'll give everybody a few minutes to think about that. Yes. Yeah, hold on a sec. Is that, I guess you can't really see the sequence of the amino acids. Let me, what if I make it super tiny? That's not working. I don't know what that's going to do. Unhelpful. Hold on a second. I'm just struggling here. Not great. Sorry, I'm having a surprising number of technical difficulties. It's really uncooperative. Okay. Yeah, this is like super tiny. Alright. Hopefully everyone has already written down the sequence of our 7-peptide amino acid. It's arg, asp, cis, tyrosine, glutamine, valine, glutamic acid. So you can hopefully see everything now. I'll give everybody a couple more minutes if you haven't already solved it by the time I finish projecting this. Alright, so let's go over this one. So first of all, which amino acid here has an ionizable, or what are our ionizable functional groups that are in this peptide? Yeah.
Arginine, aspartic acid,
Yeah, arginine, aspartic acid, glutamic acid. Yes, not glutamine. And is there anything else aside from these three side chains that would also contribute to charging this peptide? That is true. But yeah, if let's say we're not at a pH of 7, it's also really important to think about our terminal carboxyl group and our terminal amino group, right? So at pH 7, we know that for most of our terminal amino groups, right, where the pK is around 9 or 10. pH 7 is below that. It's going to be protonated, so it's going to be positively charged at pH 7. For our carboxyl group at the end, we know that those are all usually around 2. Their pK, so at pH 7 or above the pK, it'll be deprotonated, so it'll be in this negatively charged form. So yeah, at pH 7, these will be kind of combined together and add up to 0, +1 and -1. So what are the pKs of our 3 ionizable side chains? I guess that wasn't in our list of amino acids. But we have arginine, right? Is arginine acidic or basic? It's basic, right? It's got like an amino in there. So those tend to have pretty high pKs. So at pH 7, would it be protonated or deprotonated? Yeah, most likely protonated. So that would give us some kind of positively charged amino group. So it's going to give us a +1 charge. What about our aspartic acid? What? It's an acid. Yeah, exactly. So it has some kind of carboxylic acid functional group. Is it protonated or deprotonated at pH 7? Yeah, a good guess is it's deprotonated because carboxyl groups have low pKs, below 7, almost always. So it's going to be deprotonated because pH 7 is above the pK. So we should have a -1 charge. And what about our glutamic acid? Yeah. Yep. Yeah. So we're just talking about the side chain here. So like if you think about what a peptide looks like, right? This is all drawn on, but like you get the idea, right? There's the actual amino groups and carboxyl groups participating in the peptide bond are no longer getting protonated and deprotonated. It's just the terminal ones, the C terminal and the N terminal that we have to consider. For everything in the middle, we just have to consider the side chains. So, yeah, so in the case of glutamic acid, it's on the end, so we would think about its carboxyl group, but we sort of already discussed that in the first part. Yeah. 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 Yeah, let's look at it again. Yeah, so arginine. Mm-hmm. I don't think so. Yeah, it's just one of them. I think it's just the one on the end. Yeah, yep. So, yeah, so for our glutamic acid, just to finish out this question, it also is a carboxylic acid as its side chain. And so at pH 7, are we going to be above or below its pK for a carboxylic acid? Above. So are we protonated or deprotonated? We're deprotonated. Yeah. So our glutamic acid will also have a charge of -1. So we have our positively charged terminal amino group, our negatively charged terminal carboxyl group, our 3 ionized side chains. So what is our total charge on our peptide? Yeah, so our total charge is -1 because we have 2 pluses and 3 minuses at pH 7. And how many charged groups are there on this peptide in total? What? 5, yes. So we have our 3 side chains plus our terminal amino group and our terminal carboxyl group. We have 5 total charged groups here.
So we always count those 2 extras?
Yep. Because it does depend on the pH, right? So like at pH 7, they are both charged. At some pHs, like low ones or high ones, those functional groups might not be charged. So it's important to think about them.
If we're given something like this, we're told different pH do we assume 2 and like 9 to 10?
Yeah, yeah, yeah. Yeah, it won't be like guess at 9.5 which one it is. Like it'll be obvious. Yeah.
Whenever it's at, just so it's kind of like whenever it's at Savage, always add those two.
Yeah, so in general, regardless of the pH, always think about the N terminus and the C terminus. So like let's say you're at pH 1, right? Then everything's protonated. So in that case, your terminal carboxyl group would be protonated, it would be neutral. So you got to think about it because it depends on the pH whether it's charged or not. Yeah. Any other questions about charges and peptides and all that stuff? Oh, I just broke my pen. Great. Yeah. It's not, that's the number of charge groups. Sorry. Yeah, the question isn't misleading or a little misleading. This is charge groups. Yeah. Any other questions? Yeah, the net charge is -1. All right. So let's move on to chapter 5. We love proteins. Just really quickly pause the recording.